So the next disadvantage of dynamic CMOS logic is charge sharing problem. So better I'll explain the charge sharing problem with an example. Consider a 3-input NAND gate. So we are implementing the 3-input NAND gate by using an NMOS network. So there are three NMOS transistors are connected in series. So you will be getting a 3-input NAND gate, and it is implemented in dynamic logic. So you have header transistor and a photo transistor, both fed up with a clock, same clock, and then the output output node is A, that is with the capacitor CL is connected. And now see, each of this junction is associated with some capacitance C1, C2, some small capacitance are there. So now let's see how does it work. Now consider that A is equal to 1, B is equal to 1, and C is equal to 1. All transistors are on. So if all the transistors are on, initially when the clock was 0, this is your output, this output was pre-charged to VDD, right? So what is your output voltage? So the output was pre-charged to VDD. So the charge at the output, you can write it as CL, this capacitance CL multiplied by VDD. This is the charge at the output terminal. So, and all the transistors are these, and all on means these NMOS transistors are strong enough to pull this high output to 0. So this is fine. So now think about the case that when A is equal to 1, B is equal to 1, and C is equal to 0. A equal to 1, B equal to 1, C equal to 0. So this transistor will be on, this transistor will be on, and this will be off. So this is 0 means this transistor is off. And this is 1 means this is on, this is on. So these both transistors are on and these transistors are off. So then already the charge accumulated in your CL. Charge accumulated in CL will be now redistributed across C1 and C2 because C3 is off. This is off means there is no effect for C3. So the charge accumulated in CL will be redistributed as C1 and C2. So let me just draw that. See, this is your CL. Just drawing that CL. Now CL and C1, it's connected through the transistor A, which is acting as a switch, right? So CL and C1, which is connecting to this transistor A. So this is a switch. If the A is equal to 1 means the switch is on, means switch is closed. A equal to 0 means switch is open. So whatever. Now this is connected to C2 through the transistor B, and it's connected to C3 through the transistor C. So this is C, this is the transistor B. So now we are taking the condition A equal to 1, B equal to 1, and C equal to 0. So now this is closed, A equal to 1. This is also closed. This is also closed. So if these two are closed, that means these two are closed means your charge CLVDD, the charge stored in the capacitor CL will be redistributed across C1 and C2. So for example, I am assuming a voltage V, after redistribution a voltage VA will come here. So that means equal to VA multiplied by, so now the capacitors are CL and C1 and C2 will include in that when A equal to 1, B equal to 1, C equal to 0 case. So now how much will be your VA? So we'll just write VA now. VA is now it is CL into VDD divided by CL plus C1 plus C2, right? So now suppose that if you are taking your C1 is equal to C2 as 0.5 times VL. So how does it become? How much become your VA? VA is CL into VDD plus divided by CL plus 0.5 CL plus 0.5 CL. So it will be nothing but it will become VDD divided by 2. So that means actually one of the transistor is off, still you, because then also your NAND gate output should remain 1. But 1 means it should remain VDD. So now how much you got, because since the charge is now redistributed across C1 and C2 also, your VA, the voltage VA, the VA is the voltage across this. This VA become VDD by 2 instead of VDD. I was supposed to get to VDD and it is now dropping to VDD by 2. So because of the parasitic capacitors present in the internal node, the charge that the load capacitance was holding at the pre-charge time is now distributed across to other parasitic capacitors. That will cause the reduction in your output voltage. So naturally your output voltage level will degrade, and instead of VDD, once it goes VDD by 2, or again if it is reducing, it may treat it as a 0 for when it is connecting to the next stage. So it may interpret as a wrong output because of the charge sharing problem. This is what is called charge sharing problem. So now how to overcome the charge sharing problem. So for overcoming the charge sharing problem, if you connect a weak PMOS circuit or a pseudo NMOS circuit, it's just behaving like a pseudo NMOS. So a weak PMOS circuit, if you connect parallel to the header transistor, here we are connecting the header transistor in the dynamic logic. Parallel to that, if you connect a weak PMOS circuit. See, weak PMOS or his gate is always grounded so that this transistor will be always on. So now your output is all at the pre-charge phase, your output is charged to VDD, isn't it? And now even though there is a charge sharing problem or charge leakage problem, with that it will not, because since this transistor is always on, it will not allow your output to drop from VDD. So that is the advantage of adding a weak PMOS circuit always, or a weak PMOS which is on always, to parallel to this output, this circuit. So the problem is, since it is always on, when you are in the evaluation phase, when your NMOS networks are suppose on and you want to get a 0 output over here, and the NMOS network is on, you will get a 0 output because NMOS is strong enough to pass. But the problem is, it has to fight with the current flowing through the NMOS, because at the same time this is also on, there is a static power dissipation. There is a direct path between VDD and ground. All these are on and this is already on. So there will be static power dissipation. So to avoid that, if you connect a weak PMOS but its input is not, gate is not grounded, instead of that with an inverter, so your output will go to the input of your weak PMOS through an inverter circuit. So whatever be the output, it will invert and go here. If this is the way you connect the circuit, you are adding an extra inverter also and connect your gate of this weak PMOS to the output, then this static power dissipation problem will be solved. You see here, when the pre-charge phase phi equal to 0, your output will be pre-charged to VDD. So at the same time, pre-charge to VDD means the input of this transistor. So this is VDD, inverter will be 0. So the input of this PMOS will be 0. This also will be on. So it will help your pre-charge phase to maintain the output to VDD in the pre-charge phase. So in that way it will be helping your pre-charge transistor. Now what will happen at the evaluation phase? Suppose by any chance in the evaluation phase your output to become 0. So the moment output becomes 0, the input of this PMOS will be 1, right? So when it is comes input as 1, this PMOS will be off. So of course in the evaluation phase, it will not fight with the current that is flowing through the NMOS network. So in that case, we are avoiding, we don't have the static power dissipation problem. So by using this circuit, by using a weak PMOS, added up a pull-up network and which is being connected to the input is being connected to the output of the circuit through an inverter, you are even overcoming the static power dissipation problem. At the same time, it will help in maintaining the voltage at the output without affecting the charge leakage or charge sharing problem. So this is a way we can overcome the charge sharing problem or even charge leakage problem in dynamic CMOS gate. So now we will move to our next disadvantage. Next disadvantage is clock skew problem. Clock skew problem arises when we realize multi-stage circuits. See, consider this circuit. You have two stages are here, both connected in the dynamic logic. Now see, all are fed up with the same, all transistors are fed up with the same clock, right? 5, all transistors are, but this is the ith stage, this is the I plus 1, next stage. So now clock skew problem arises because the delay due to resistance or parasitic as capacitance associated with the wire. And always remember this delay will be proportional to the square of the length of the wire. So if the length is more, delay will be more. So now suppose you imagine a situation, the clock reaches first in the second stage and later after that only in the first stage clock reaches. So what will happen if the clock first reaches in the second stage? So I'm just drawing this again, same thing only shown over here. This is your clock. The moment phi equal to 0, it is recharge phase. So this is a clock on ith stage. And this is the clock reaches in the I plus 1 stage. Suppose you see here, I plus 1 stage, your clock reaches first. Then ith stage. So here it will become 1. The moment the clock become 1, what will happen? Evaluation will start. Which stage? The second stage evaluation will start. At the same time, what about the first stage? Still it in the pre-charge phase. Still in the pre-charge phase. So pre-charge phase, your output will be fed up to 1. It is keeping us 1 in the pre-charge phase. This 1 only will come as the input to the second stage. And at the same time, in this position, evaluation already started. Suppose second stage is a inverter. Okay. The moment this one comes here, what will happen? This transistor will on. This was pre-charged to VDD. When it is 1, that will be discharged to ground so that you will get your output as 0. But here in the evaluation phase, but here it's not yet done the evaluation phase. But after this time, the evaluation starts over here. Your actual output, this NMOS are on and actual output is 0. So this is your actual output of first stage. By the time the 0 comes over, it was already pre-charged, was here VDD, that is discharged already, and now your output is 0. So now it cannot again taken back this output to VDD. So when the clock reaches in the later stage before the preceding stage, and the evaluation already happened in the latter stage. So which may lead to a premature discharge of load capacitor and resulting in an incorrect output during the evaluation phase. So this problem, if you want to overcome this problem, we have to provide, means in the evaluation phase, even though it starts first here, you are keeping your output low. Instead of 1 in the pre-charge phase, you are keeping your output low. This will not happen. So always if you connect the stage 1 output with a inverter, that's what is happened in dynamic domino gate. So domino CMOS gate will overcome clock skew problem.